Good morning, good afternoon, everyone. I'm Hoang from Budapest University of Technology and Economics, Hungary. Today, I'd like to present the topic of constrained finite element method with space mapping. This is the presentation outline. I'm going to make a brief introduction which follows by the space mapping concept and methodology. Then I'm going to show some numerical examples and the summary will end my presentation. The buckling phenomenon of thin wall member is complex due to various possible buckle modes and their interactions. These buckling modes have different impact on the capacity of the members. For example, local buckling has some reserve capacity while the global has not. Thus, in most of the design specifications, these phenomena are discussed separately. Being able to analyze these buckling modes separately is logical and crucial for designing of thin wall members. Model decomposition allows us to separate the buckling into global, distortional, local, and other modes. Currently, there are few methods which have a capability to do the model analysis, such as the generalized beam theory (GBT), the constrained finite strip method, the CFSM, the constrained finite element method, the CFEM, and the energy-based approach. Here, I just focus on the CFEM. The constrained finite element method, CFEM, is a shell finite element calculation with a model decomposition ability. The displacement space is separated into the GDLO, which is the global, distortional, local, and others displacement space, respectively. These separations are done by using the mechanical constraints within each element. Thus, this displacement field can be considered as the alternative basic system. Mathematically, the model decomposition is a construction of the Rm constraint matrix, which transfers the displacement vector from the normal basics to the model basics. And the solution of the buckling problem is the solution of the generalized eigenvalue as shown in these equations. The CFE element is the flat rectangular shell element with specific shape functions based on the Kirchhoff-Bley theory. The interpolation functions different in direction, the longitudinal and the vertical are shown in these figures. This special set of shape functions allows the mechanical criteria for model decomposition to be exactly satisfied within each individual element. However, it also causes some potential drawbacks as the highly rectangular mesh is needed and the comparison to the Reisner-Mindling elements, which are commonly used in the commercial software, are difficult. We want to do the model decomposition for the non-rectangular element as well as the Reisner-Mindling shell element, and the concept of space mapping for constrained finite element method is created. The idea is that the physical domain is approximated using two different discretization systems using different finite elements. One is the ordinary shell element, the other is a specific CFEM element. In the ordinary shell element system, all stiffness matrix load vectors are generated. Technically, it is used to directly solve the problem. As the model decomposition is performed, the constraint matrix Rm to the certain buckle mode is needed, and this Rm matrix is firstly constructed in the CFEM element base and then mapped into the ordinary basis system. With the help of the mapping, the whole model decomposition process can be applied for the ordinary shell element as it is for the CFE element. The mapping procedure is performed as follows. Each column of the Rm constraint matrix in the CFEM base is in fact one displacement vector. Each displacement vector then is approximated in the ordinary basics as a displacement vector using the operation which take the shape function of the CFE element and the nodal displacement in the CFE basics as well as the nodal position of the ordinary basics. It can be written in the mathematic form like the one shown in the slide, and in the case of the mesh of the ordinary element is defined, this whole process can be shown as a more compact form. Here, where the d ordinary is the displacement in the ordinary basics, and the d CFEM is a displacement in the CFEM basics, and the M map is a mapping matrix. The two approaches for the mapping were tested. One is the condensation, where only the translation DOF, the degree of freedoms, are mapped, and the other is non-condensation, where both translation and rotation DOF are mapped. In next slides, I would like to show some numerical examples applying the previously discussed concept. In these examples, linear isotropic material is assumed, uniform compression load and simple support are applied, linear buckling analysis is performed, and constrained to three scenarios: global buckling, distortional buckling, local buckling. Two ordinary target elements, the quad A and quad 4, condensation and non-condensation approach, several meshing configurations, and in each example, question of whether it's possible to use condensation, how much mesh density affects the result, and how much mesh irregularity affects the result. We developed two ordinary shell elements for this concept. The quad 4 and quad 8 are quadrilateral shell elements with the Reisner-Mindling plate theory base with 4 and 8 nodes similar to the ANSYS 181 and 281 respectively. As there are several of mesh configurations, we name them as follows. Each configuration has three letters. The first one is related to the mesh irregularity. The second one is related to the mesh density with respect to the density of the CFEM. For example, the RDM means regular double mesh. Here are some mesh configuration figures. This is a configuration for constraint to global buckling. With quad A element, the mapping results are very good. As you can see in the table, the buckling factor for the first 10 modes are shown, and if the number is green, its value is within plus minus 5% of the CFEM result. If the difference is bigger than 5%, then the color is red. For this example, the condensation is applicable. The effect of the mesh density is negligible as well as the irregularity. For quad 4, as you can see from the table, the mesh density and the irregularity has significant effect on the result. The mesh needs to be dense enough to have the good result. Here is a configuration for constraint to distortional buckling. For quad A in general, the mapping results are good. As you can see, there are not so many red numbers in the table. However, the mesh irregularity has some negative impact on the result. For quad 4, it's not very good result. As you can see, almost all of the results are red, except few cases where the meshes are regular and the modes are small. Here you can see some buckle shapes of the first distortional mode of different meshing configurations. It can be seen that with quad A elements, the irregularity doesn't change the buckle shape compared to the original CFEM. However, with quad 4, the irregularity not only gives big difference in terms of the load factor, but also result in a wrong buckle shape. Here is the configuration for local buckling. For quad 8, it is clear from the table that the condensation approach is not precise for the local constraining. Almost all of the result is in red. However, the non-condensation shows a very good agreement with the original CFEM result. As you can see in the table, for the non-condensation, all of the results are in green color, and the effect of the mesh density as well as the mesh irregularity can be neglected for the non-condensation mapping. For quad 4, the mapping results are poor even with the non-condensation approach. It also shows the significant effect of the mesh irregularity to the exactness of the result. Alright, finally I would like to briefly summarize today's presentation here. In this presentation, I've introduced the idea and concept of the constraint finite element with space mapping. The idea is already implemented and used for testing some basic numerical example. As the numerical result have shown, some conclusions can be made as the quad 8 largest element is better than the quad 4. The denser the finite element mesh of the ordinary element is, the more accurate the results are. The irregularity mesh introduces some inaccuracy to the result, and the rotational degree of freedom is important for the local buckling. This idea is very promising, and of course further investigation is needed. And with this, I would like to end my presentation, and thank you very much for your attention.